So once again, welcome to all. So today's session we will be dealing mostly with turbines, which also comes in the fifth module. So before going to the detailed discussion, these are the objective of today's session. So first we will discuss the general layout of an hydroelectric power plant. Then definition and classification of hydraulic turbine. After that, we will discuss the major difference between an impulse turbine and a reaction turbine. Then we will go to the parts and working of Pelton turbine, parts and working of Francis turbine, and the last one, parts and working of Kaplan turbine. So these are the three turbines, very important, which comes in your syllabus. So you have to study at least these three turbines. And finally, we will discuss the efficiency of a turbine, how to calculate efficiency of a turbine. So these are the objective of today's session. So let's discuss what is the general layout of an hydroelectric power plant. So these are the components of a general hydroelectric power plant. So what are the major components? So mainly four components are there. So first one is a dam. So already we know a dam is constructed across a water body, a river, ocean or something like that, to collect water and increase the head or increase the potential energy. We are using a dam. So that is our first component. Then our second component is a penstock. So what do you mean by a penstock? A large diameter pipe of very huge length carrying water to the turbine is called a penstock. And these are made of steel or reinforced concrete. So you can see here, this is the penstock of this power plant. Then third one is of course our turbine. So whether it is Pelton turbine, Francis or Kaplan, a turbine is a main component in any hydroelectric power plant. And what type it is will depend on several factors. And the last one is a tail race. So what is a tail race? It is a channel which collects and carries water once it is used for power production. So once the water is used, after the power is produced, we have to collect this water and carry away. And we can use it for some other purpose like agriculture, irrigation or anything else what we want. So these are the four components of hydroelectric power plant, and we will be focusing only on this third one, turbine. Now we are talking about hydraulic turbine. Turbine means it can be a gas turbine, steam turbine, several types of turbine are there, but we are talking about a hydraulic turbine. That means our working fluid will be only liquid water. So we are discussing only hydraulic turbine. So what do you mean by a turbine or a hydraulic turbine? Is a device which converts hydraulic energy to mechanical energy. So that means it is a reverse of pump. So you have already studied pump. What is a pump? So pump converts mechanical energy to hydraulic energy. But here you can see it is a reverse. It converts hydraulic energy to mechanical energy. And what is hydraulic energy? Already you know that. It is a total energy of water, which is sum of pressure energy, kinetic energy and potential energy. And what is mechanical energy? That also you know. Mechanical energy means a rotation or a work is called as continuous rotation of a shaft. We call it as mechanical energy. So that means by receiving the hydraulic power of water, the turbine will continuously rotate. It will produce mechanical energy. And what it is used, this mechanical energy can be given to a generator and it will produce electricity. That is what all the hydroelectric power plants are doing. But we will not talk about much in this generator section which comes in the electrical engineering part. So we will only focus on this turbine area. Now it's a brief classification of turbine. The first classification is according to the type of energy at the inlet. Which type of energy is available at the inlet? We can classify into two categories, impulse turbine and reaction turbine. So this is a very important classification. So we will discuss it detail in the next slide. Then another classification is according to the direction of flow through the runner. The rotating part of the turbine where the blades are connected is known as a runner. So according to the direction of flow, how we can classify the turbine? We have four classification. First one is tangential flow turbine. What do you mean by tangential flow turbine? Simply the water flows tangent to the runner. So runner means a circular shape, it's a circle, and if the water flows tangent to the runner, we call it as a tangential flow turbine. A Pelton turbine is an example of tangential flow turbine. So we will see it in Pelton turbine. What is a tangential flow turbine? So it is nothing but the water flows tangent to the runner. Then second one is radial flow turbine, and it means the water flows radially to the runner. Along the radius, the water will be flowing. So no modern turbines are purely radial flow turbine. Earlier the Francis turbine was radial flow turbine, but nowadays they are not radial flow turbine. So radial flow means the water will flow radially to the runner. And another one is axial flow turbine. So as the name indicates, here the water flows parallel to the axis of rotation of the runner. So the runner will be rotating continuously. So it is having some axis of rotation. So if the water is flowing parallel to that axis of rotation, we call it as an axial flow turbine. So Kaplan turbine will be a good example for this. And finally we have mixed flow turbine. So what do you mean by mixed flow turbine? If the water enters radial to the runner but leaves axially, we call it as mixed flow. That means two types of flow is available according to direction. It enters radially, but it does not leave radially, it leaves axially. So that is meant by mixed flow. Francis turbine, today's Francis turbine is a mixed flow turbine. So these are the four classifications according to the direction of flow. And the last classification is according to the type of head. So we have already discussed what you mean by head, what is the unit of head, etc. So according to how much meter of water head available at the turbine inlet, we classify into three categories. First one is high head turbine. What do you mean by high head turbine? It works under the head of more than 250 meter. If a turbine is capable of producing power by working under a head of more than 250 meter, we call it as a high head turbine. So automatically if the head increases, discharge will be very low. So already we know head and discharge are inversely proportional. So if the head is high, the discharge will be low. And Pelton turbine is a high head, low discharge turbine. And what do you mean by medium head turbine? If the turbine works under a head of some 45 meter to 250 meter, in that region we call it as a medium head turbine. Francis turbine is a medium head turbine. So head is medium means discharge also will be in medium range. So Francis turbine is a good example of medium head turbine. Then low head turbine, the head is very less, the works under the head of less than 45 meter. So if a turbine works under less than 45 meter head, we call it as low head turbine. So these are the another classification according to the head. And Kaplan turbine is a low head turbine. So head is low means automatically discharge must be high. So that means Kaplan turbine is low head and high discharge. So these are the major classification of turbine. And now we have to focus on this. What do you mean by impulse turbine and reaction turbine? What are the major difference between these two turbines? So this is a simple figure of an impulse turbine. This is a simplified figure of reaction turbine. So find out what is the difference here. You might have find out some difference. So let's check what are the difference. Yes, as the name suggests, what do you mean by impulse? So impulse means, we already in the physics we have studied it. Impulse means a force, large force for a short period of time acting on a particular object. We call it as impulse. So here the turbine runner and is rotated by an impulse of water jet. So you can see here the water is coming through the nozzle and hits the blade of this impulse turbine, the runner. So these are the blades, we call it as buckets in impulse turbine. So these are the blades of this turbine. So water hits the one blade, it rotates, the next blade comes, it rotates. So like that it will achieve a constant speed. So each blade is acted by a large force for a short period of time. So that is why we call it as impulse turbine. So it is rotated by the impulse of water jet coming through a nozzle and hitting the buckets one by one. And what is the energy available? What is the energy available here? So you know only three types of energy is there for a water: potential energy, kinetic energy and pressure energy. Already when moving through the penstock, potential energy is decreased when it reaches here, so it will not be there. Then kinetic energy and pressure energy, as this is open to atmosphere, the water coming through the nozzle is open to atmosphere at this region. So pressure will be only atmospheric pressure. So major energy in impulse turbine is kinetic energy. This is very, very important. The energy available at the inlet of impulse turbine is only kinetic energy. And that means pressure remains constant. The pressure is only atmospheric pressure. So before heating and after heating, the pressure remains constant in impulse turbine. It is just atmospheric pressure. So this is impulse turbine. Now see what is the difference in reaction turbine. As the name suggests, reaction turbine is moved by the reaction of water. So you can see here there is no hitting of water here, but the water is moving through the nozzle or through the blades on the runner and rotates by the reaction. So you can see here the water is ejected or moved in this direction, that is in the anti-clockwise direction. So automatically the rotor will be rotating in the clockwise direction. So here the reaction is rotating the turbine. So you just recollect the recoil of a gun. When you are firing a gun using a gun, the gun will move in the opposite direction. So similar thing is happening here. By Newton's third law, we are forcefully ejecting water through the blades on the runner. So here these are the blades. We call here it is nozzle, marked as nozzle. So these are the blades of turbine. So water is moving through the blades. It is not hitting the blades. So that means it moves by the reaction of water through the blades on the runner. And another thing is here the runner will be full of water. What means what is the energy available at the inlet? What will be the energy when entering water? It is full of water means it is enclosed in some casing and it will be completely full of water. So the pressure will be not atmospheric pressure. So here that the inlet, the energy is not only kinetic but pressure energy also is there. This is another important point. The energy available at the inlet of reaction turbine is kinetic energy as well as pressure energy. So both this energy will be there. But when going to the outlet, this pressure energy decreases. That is another point. From inlet to outlet, the pressure energy goes on decreasing. So you can see here the major difference. First one was it works by the impulse of the water jet coming through a nozzle, but here it is work by the reaction of water flowing through the blades on the runner. And another point is the energy available is impulse turbine only its kinetic energy, but here kinetic energy as well as pressure energy is available. And the last point is impulse turbine, the pressure remains constant from inlet to outlet, it is atmospheric pressure. But reaction turbine, the pressure energy is going to decrease from inlet to outlet. So these are the major difference between impulse turbine and reaction turbine. Now we will go to the first turbine, that is Pelton turbine. So what is a Pelton turbine? So this is a figure of Pelton turbine. So in every turbine you have to neatly draw their figure, because working means you have to draw a neat figure. So hope some of you have already drawn an assignment. So this is the Pelton turbine figure. So Pelton turbine is a tangential flow impulse turbine. So you can see here, this is our runner, this circle. The water is going in this direction. So it is tangent to this circle. So it is a tangential flow impulse turbine. So it works by the impulse of jet. So it is a tangential flow impulse turbine. And it is named after American engineer L.A. Pelton, who developed this turbine. And water strikes the bucket along the tangent of the runner. And as it is an impulse turbine, the energy available in the inlet is only kinetic energy. The pressure at the inlet and outlet of atmospheric pressure only. So these are the Pelton turbine. And it is used for high head and low discharge. So already we have discussed Pelton turbine is an example of high head turbine. So that means 250 meter and above it can utilize water head. And discharge will be very low. So you can see here only a jet of water is required. The quantity of water is very less. So we will go to the parts and working in detail. So mainly 4 parts. The Pelton turbine we can divide into 4 major parts. What is the first part? This nozzle and spear. So at the end of the penstock we have a nozzle, a shape like this, through which water coming out. So this is known as a nozzle. And what is this spear? This one. What is spear? Spear is a conical needle. So this is a conical needle at the end like this. And it can be moved forward and backward either by a hand wheel attached here or by some automatic arrangement. So that means it can move in this direction, axial direction. So spear is a conical needle which can be operated by a hand wheel or automatically in axial direction, this direction. Then what it is used? As it is mainly used for controlling the water. So if you want to vary the water for load or some other applications, we have to reduce or increase the water. This spear will act. So it is mainly used for controlling the water striking the buckets. So the blades of an impulse turbine we call it as buckets. Then how it is controlling the water? Yes, if the spear is pushed forward, so in this position it is completely open. This opening of nozzle is fully open. And now if you push this spear towards the right, this will block the flow and it will be reduced. The amount of water will be reduced. And similarly, if we are pulling it back towards the left, the amount of water will be increased. So there is a simple technique used for controlling the water flow to the runner. Then we have second part, major part, that is runner with buckets. So runner means this nothing but a circular disc on the periphery of which a number of buckets, number of blades are connected and there are equal distance. So each buckets are having evenly spaced. And the shape of the bucket in Pelton turbine is a double hemispherical cup shape. So we will see that figure later. So it is a double hemispherical cup shape, and at the center we have a splitter. So each bucket will be a cup shape, double hemispherical cup, and at the center of that we will have a splitter. So that will split it into 2 equal parts. So when the water is striking, it will be first strike the splitter and water will be divided into two parts and water will deflect through 160 degrees. So water, now if this is our initial striking, so after striking it will split into two equal parts, then it will reverse. So it is almost equal to 180 degree. So the water is, the rate of momentum change is in the 180 degree, near 160 to 170 degree. So this momentum change will help to rotate the runner. So we know that by Newton, so the rate of change of momentum is the force. So this will be the impulsive force. The rate of change of this jet will exert an impulsive force and the runner will rotate. And the buckets are made of cast iron, cast steel or stainless steel, made of these type of materials according to the head available. Now we are going to the third part, that is casing. So what is this external casing? We have this casing. What is the function? So Pelton turbine does not have that much function. So here its function is to avoid the splashing of water. So water will be splashing. So just collect that splashing of water and discharge it to the tail race. So tail race will be at the bottom. So its function is only this. And they are made of cast iron or fabricated steel plates. And it does not perform any hydraulic function here. So we will see it in Francis turbine. It is having a very good hydraulic function, but here it does not have any function. So that is our third one. Then finally we have the fourth component, this brake jet or a brake nozzle. We can see here a small nozzle is provided. So what is the function of that? So even though if we are completely forward, we are pushing the spear in the forward direction and we are completely stopping the water, the turbine will not stop instantaneously. Why? Because we know that by inertia the runner will revolve for a long time. So what do you mean by inertia? Suppose you are switching off a fan. If that will come to rest instantaneously? No. So it will rotate for some 1 or 2 minutes, then only it will stop. That is due to inertia. So this turbine will be rotating very high speed. So if we want to stop the turbine and we are pushing the spear forward and we are completely stopping the water, even though the turbine will be running for a very long time due to this inertia. So for stop it with a short time, we are providing a jet in the opposite direction, a small jet. So your turbine is rotating in anti-clockwise direction by this here anti-clockwise. So we will provide a small jet in the clockwise direction. So that is the function. To stop it in a short time, a small jet of water is provided on the back of the turbine blades. And it is known as the brake jet or a brake nozzle. So these are the 4 components of Pelton turbine. And you can see this is a real Pelton turbine. These are the buckets. These are the nozzle and spear will be inside. So your casing is removed for view. And these are a single bucket. So you can see here it is a double hemispherical cup shape with a splitter at the center. Though that is the shape of each bucket. So it will just like 2 spoons. If you are putting 2 spoons together, or it will be like that. So now we will go to Francis turbine. So this is an entirely different turbine. So this is a front view, and this is the front view, and these are the top view, or other way also. Now what will be the Francis turbine? It is a mixed flow reaction turbine. So already we have discovered what is mixed flow. The water will be entering radially to the runner, but it leaves axially. We call it as a mixed flow. So here you can see the water is coming through the penstock, this blue arrow. Then it enters, this is our runner, this circular disc, and it will be entering in radial direction, parallel to the radius of the runner. But wherever it is going, it will be leaving only in this vertical direction, that is axially. So that means this is known as a mixed flow reaction turbine. It is also a reaction turbine. And it is named after J.B. Francis, an American engineer. And as it is a reaction turbine, the water possesses kinetic energy as well as pressure energy. And pressure energy will be going decrease from inlet to outlet. So inlet pressure will be high. So this is at the inlet of the turbine, pressure will be very high. But when we are going to outlet, it will decrease and kinetic energy will be more. And they are used for medium head and medium discharge applications. So head will be between 45 to 250 meter only. Now we will discuss the parts and working. So similar to Pelton turbine also, here we can divide it into 4 parts. First part is casing. But what is the importance of casing? Yes, here it is having a particular shape, that is spiral shape. And the area of cross section, you can see here the area of cross section decreasing from inlet to outlet. So that means it is a reverse of centrifugal pump. So already you have studied centrifugal pump. Centrifugal pump also have spiral casing, but its flow direction is the reverse. In centrifugal pump, the water enters axially and leaves radially, but here it enters radially and leaves axially. So that means it will just look like a centrifugal pump's casing, but the flow is, direction is different. So when it is going from inlet to outlet, its area is decreasing. So that means it is having an hydraulic function. And it will be full of water. The casing and the runner will be full of water. Then only it will have pressure energy more than atmospheric pressure. So why it is full of water means then only it will have high pressure greater than atmospheric pressure. And what happens to pressure energy when it goes from inlet to outlet? It will decrease. Why it will decrease? Because of this reduction in area. So already we have discussed by continuity equation, when area decreases, velocity increases, and when velocity increases by Bernoulli's principle, pressure will decrease. So pressure will decrease from moving through the casing. And they are made of concrete, cast steel or plate steel. Now another component, second component is guide mechanism. So what do you mean by guide mechanism or guide vanes? So here there is no nozzle and spear. So how will you control the water, amount of water by this guide mechanism? So you can see here before entering to the runner, this black one, we have a set of stationary vanes and they are attached in a stationary circular wheel and they are known as the guide mechanism. So guide mechanism is a stationary circular wheel around the runner, so before the runner, and on which a number of stationary vanes are fixed. Stationary vanes means they will not move by the action of water because they are attached to a stationary wheel. So that wheel will be screwed and it will not rotate. So what are the function of this guide mechanism? The first function is to guide water. So water is entering with high pressure. So we have to smoothly guide it into each blades of the runner. So runner blade will be inside. So these are the runner blades. This small one. This black color one is the stationary vanes. So the first function is to guide water before entering the runner without shock. And another function is this one. You can adjust the gap between these two stationary vanes, any two adjacent vanes externally. So you can tilt these vanes so that this area will change. Between the distance between two vanes, we can incline or we can straight it. So that's how we are controlling the amount of water. So here the nozzle and spear in impulse turbine, in Pelton turbine, what the nozzle and spear is doing, here it is doing by this guide vane mechanism. So the width between two adjacent guide vanes can be adjusted externally and we are controlling the amount of water by that. So two functions are there. First one to guide water without shock. Second function to control the amount of water by adjusting the gap between two adjacent vanes. Now we will go to the third component. And third component is of course our runner. So runner is a circular wheel on which a series of radial curved vanes are attached. So here the vanes are on the runner, not in the Pelton Turbine. Pelton Turbine it is on the periphery of the runner, but here it is on the runner. And they will be designed so that the water will be entering and leaving without shock. And they are made of cast iron, cast steel or stainless steel. And this runner will be keyed to the shaft, and this shaft will be our power production, where we will be producing power and giving to the generator. So this central one is our turbine shaft. The runner will be attached to that shaft. Then last one, we have a draft tube. So in impulse turbine we will not see a draft tube, only in reaction turbine we will see a draft tube. So you will see in this front view what is a draft tube is. So a draft tube is a tube of increasing area. So why we require a tube like that at the outlet? So after hitting the water in the turbine and after producing this power, we have to discharge into tail race. So we already know that. So why a draft tube is required in reaction turbine and why it is not used in an impulse turbine? That is an important question. So you can see here one end of the draft tube is at the outlet of the runner, another end is submerged in the tail race. So this is a tail race. So one end is submerged in tail race, the larger end. The smaller end is at the outlet of the runner. So why we are requiring a draft tube? You already know that the pressure energy in a reaction turbine goes on decreasing from inlet to outlet. And mostly the pressure, what is the pressure at the outlet? It will be less than atmospheric pressure. So in this region, after producing power, the pressure will be less than atmospheric pressure. What is the pressure at the tail race? It is open to atmosphere, so atmospheric pressure. So we cannot discharge a fluid from low pressure to high pressure. It will have several problems. So you have to increase the pressure, then only we can smoothly discharge this water. So that is the function of draft tube. The pressure at the exit of the runner is generally less than atmospheric pressure, and therefore the water at the exit cannot be directly discharged. So we want to increase the pressure. So that is done by a draft tube. So when the area is increasing, the pressure will increase by Bernoulli's principle. We know that. So that is what the draft tube does, to increase the pressure to the above atmospheric pressure when it reaches here. So these are the four components of Francis turbine and it's working. So this is a real Francis turbine. You can see here these are the runner blades on the runner. This is our runner and blades are on the runner. This is the shaft and these are the guide vanes and these are the casing. And this is the one end of the penstock will be connected here. And this is another view. This is the draft tube at the outlet of the turbine of increasing cross section. So you can understand this Francis turbine. Now we will go to Kaplan turbine. Kaplan turbine is very easy because it is also a reaction turbine and only slight difference is there. So if you understand that difference, the other things are similar to Francis turbine. You can write it very easily. So just understand Francis turbine first, then just understand what is the difference between Francis and Kaplan. We can write it very easily. So this is a Kaplan turbine. What are any difference? Here also we have a casing is there. We call it as scroll casing. And draft tube is there, runner is there, guide vanes are there. But some arrangement is a little bit different. So Kaplan turbine is also a reaction turbine, but it's axial flow. The one difference with Francis turbine is here it is axial flow. So the water is flowing axially. So it is a vertical direction. So you can see here this is a shaft. Shaft is vertical. In other turbines it was horizontal. Pelton turbine and Francis turbine, the shaft was horizontal. But here the shaft is vertical. And water is coming through this casing and it will be parallel to the axis. So you can see here these arrows represents the flow of water. So it is parallel to the axis of this shaft. This is the axis of the shaft. So it is an axial flow and it's also a reaction turbine. And another important thing is the adjustable blades. So we can adjust the orientation of the blades of Kaplan turbine. So it is one peculiarity. The Francis turbine, we will not adjust the blades. We can adjust the blades of Kaplan turbine. And it is developed by the Austrian professor V. Kaplan. And it's a reaction turbine, so water at the inlet have both kinetic energy as well as pressure energy. And pressure energy goes on decreasing from inlet to outlet. So these are common points for Francis turbine also. And it's used for low head and high discharge. That is important because Kaplan turbine is used for low head application. When the head is less than 45 meter, it is apt for low head. So mostly the worldwide, if you look at the worldwide picture, the most turbines are Kaplan turbine because the head will be very less in most application. So in micro and mini turbine power plants, we will be using this Kaplan turbine. So if you want a small power production from a small waterfall, we can use this Kaplan turbine. So Kaplan turbine is the most widely used turbine for power production. Now the parts, here also we have 4 parts. First one, a scroll casing. So here the casing is a scroll shaped tube that wraps around the turbine. So the orientation is different. Here the axis is vertical, the shaft is vertical, and the casing will scroll around this shaft and it wraps the turbine. And it will be always full of water and pressure energy. Initially it will be high and it goes on decreasing because its area is decreasing, it goes on decreasing. And they are made of concrete, cast steel or plate steel. Then another component, here also we have guide vanes, but they are at this side, they are around this shaft of the turbine. And here also the function, they have 2 functions. One is to control the quantity of water. By changing the orientation, we can tilt or change the orientation of these guide vanes, and that we can control the amount of water entering to the turbine. So now we have the third part, that is the runner. So here we have a major difference. Here the shaft rotating part of the turbine is connected to the shaft of the generator. So that means here the shaft itself is the runner. No circular disc is here. So you can see here the shaft itself connected to the runner, but the one end of the shaft is larger in diameter. You can see here the shaft is smaller, but when reaching here, it will have some larger diameter section, and this is called as a hub or a boss. So you can see here hub means the lower end of this shaft is having larger diameter, and that is known as a hub or a boss. And the vanes are on this hub and they are adjustable. That is another important thing. We can change the orientation manually, and they are adjustable vanes. You can change the angle. And here also we have a draft tube because the reaction turbine, the pressure will be less than atmospheric here. Tail raise, the pressure will be atmospheric. So we will not directly discharge the water. We have to use a tube of increasing cross section. So a tube of increasing cross section is used, and one end of the draft tube is connected to the outlet of this hub. Other end is submerged in tail raise. So all these are common points for Francis turbine also. So these are already discussed. The pressure at the exit of the runner is less than atmospheric pressure, and we have to, we will not directly discharge water to the tail raise, and passing through the draft tube, the pressure will increase above atmospheric pressure. And this is a real Kaplan turbine hub, propeller of Kaplan turbine or the runner of Kaplan turbine with the blades. These are the blades. and this is it will be very huge or it can be very small also. So this is a huge Kaplan turbine produced by General Electric. So you can see here these are the guide vanes. This is the vertical shaft and this is the lower end of the shaft with this propeller. So with this we are completing all the 3 turbines. Now we are going to the final section, how to calculate the efficiency of a turbine. So already we have discussed how to calculate the efficiency of a pump. So it is very easy. The efficiency means just output by input. So what is the input of the pump? What is the input energy? Hydraulic energy. So input power of a turbine is hydraulic power. So we have already an equation in rho QGH. So input power can be calculated by this equation rho QGH. So rho is the density of water, constant 1000 kg per meter cube. G is acceleration due to gravity, another constant 9.81 meter per second square. Then only 2 parameters are there, Q and H. What is Q? Yes, discharge or the amount of water flowing to the turbine in 1 second in meter cube per second. The SI unit of discharge is meter cube per second. So it is the amount of water flowing to the turbine. And H you already know it is the net head of water available at the turbine inlet. So how much head is available? How much water head? It is a measure of energy. So how much meter of water head is available at the turbine head inlet? So that are 2 parameters we want to know for calculating input power. So what is output? Output is mechanical energy. So it will be the power produced by the turbine. So it will be given in the question, what is output power produced by the turbine. So it will be in SI unit, must be in watt. So if it is in kilowatt, you have to convert into watt, or if it is in megawatt also, you have to multiply by 10 raised to 6, 10 to the power 6. So like that, the output power and input power must be in the same unit. Then efficiency is simply output by input into 100%. So it's a simple calculation. Just you have to study this basic equation for hydraulic power rho QGH and substitute Q and H in SI units and find out output power. It will be given and just divide and convert into percentage. So with this we are stopping this session. So it's a very important topic. So try to study the figure and try the working and what are the difference between each turbine. And for more understanding, just visit the animation videos available at the description box. Thank you.